As we continue our study of radicals, we're now going to take a look at binomial radical expressions. So you have to think about like terms when you think of like radicals. Like radicals are radical expressions with the same index and the same radicand. So I put some simple examples up here. Notice these two are both square roots and they both have a 2 underneath the square root. So that means they are like radicals, but when we add them, we're adding the number in front, the 3 and the 1. So that's where that 4 is coming from. Notice that the radical didn't change. For subtraction, here I have a third root of 7 and a third root of 7. So those are like terms. So when I take the 5 minus the 1 that's sitting here, I get 4 cube root of 7s. The radical itself does not change. So you can think of that radical as a type of variable. We're adding and subtracting those variables. The variables themselves don't change. Just like if we would take a 2x plus a 3x, we get 5x. The x itself doesn't change. As long as what's underneath the radical and the index, so the radicand and the index have to be the same, we can add the numbers out front. So 8 plus 1 gives me 9 of those square root of 5xy's. And for subtraction, again, the radicand here is 9x squared y. The index for both of these is 3, so they are the same. That's why we can take the 1 minus the 8 and get negative 7 with that cube root of 9x squared y. The way we actually combine these radicals is we use the concept of the distributive property. And again, this works both directions. So if I have two radicals that are the same, I can add and subtract the b in front. The radical itself does not change. Or if I have a sum, I can break it into two separate radicals. Same thing for subtraction. Two separate radicals here, as long as the radicals themselves are the same, I subtract the a and the b. Or if I have something that's together, I can break it into pieces. So let's go through some examples and see how this works, see if we find any that don't work. Looking at this one, and I notice that underneath the radical is an xy, so the radicands are the same. These are definitely both square roots, so we're going to add the numbers in front. I have 3x plus 4x, that gives me 7x. The radical itself does not change. On number 2, they're both square roots, that's good, but I see that this is a 5 and this is a 7. Because those radicands are not the same, I cannot do this problem. You can't combine those. Those are not like radicals or like terms. The last example for addition, I've got a 7bc, so the radicands are the same. These are both square roots, that's great. They are like terms. 14a plus 5a, that gives me 19a. And my radical itself does not change. I still have a square root of 7bc. For subtraction works the same way. I'm going to look and see if the radicand's the same. These both have a 5x. That's a good start. This is a square root. This is a cube root. I cannot do this one. There is no solution here. If I look at number 5, I've got a 7xy and a 7xy. That's a great start. This is a fifth root. This is a third root. I cannot combine those things. There is no solution here. If they were both the same, if these were both fifth roots, no problem. But they're not. Can't do it. Number 6 I can actually do. They're both fifth roots. That's great. They both have a radicand of 3x squared. So I have fifth root of 3x squared. So my answer is going to have a fifth root of 3x squared. I just need to take the numbers in front and subtract them. Now, we're going to get into more complicated radicals that we want to simplify. And at first glance for number 7, this looks like a problem that can't be done. They are all square roots. They all have a square root, but none of the radicands are the same. So you might be tempted to say there's no solution, I can't simplify this one. But let's dive in a little closer. Let's take a lesson from our multiplication and our simplification of these radicals. I can break this 12 down into a part that I can do, part that I can't. So I'm going to do that. I can break the 75 down. Something I can do, something I can't. Nothing I can do with the 3. But now we're going to take a second look at my expression. They're all still square roots. And now the radicand is the same for all 3 of them. They're all 3's. So now I can take the numbers in front. 2 plus 5, that's 7. Minus 1 leaves me with a 6, square root of 3. So at first glance, it looked like an expression we couldn't do anything with. If I do a little simplifying first, it turns out that I can. And they can get more complicated, of course. Here I've got a 28. I'm going to go 4 and 7. Here I've got a 175, a 25 and a 7. And for 63, a 9 and a 7. And some of you are already seeing, oh, we're going to have the same radicand here. We're going to be able to do this. So I've got a 2 square root of 7 minus a 5 square root of 7 plus a 3 square root of 7. So just by doing a little simplifying of my radicals, which we've been practicing, now I can simplify this because they are all like terms. 2 minus 5, that's negative 3. And negative 3 plus 3, that's 0. So technically my answer is this, but I don't even need the square root of 7 because 0 times anything is just 0. Now let's take a closer look at these binomials. Let's try to multiply them and divide them. So just like any other binomial, when we want to multiply these out, we use the FOIL method or the box method or a modified distributive property. So I'm going to go ahead and FOIL this one out. 4 times 5, 4 times 4 square root of 2 would give me a 16 square root of 2. I'm just multiplying the numbers in front. Multiply the numbers in front here and the inside, so I get a 10 square root of 2. And then I have this guy. So I'm multiplying the 2 times the 4, that gives me an 8. And here, I multiply what's underneath, and I get a 4. Okay, that's just the FOIL process. But now I have some simplifying to do. These are definitely like terms. So I'm going to put those together. And this turned out to be a radical that now I can do. So the square root of 4 is 2, and 2 times 8 makes this 16. So I have like terms here, and I have like terms here, which I just talked about. I would have 26 of those square root of 2's. So a little simplifying there. Now if you prefer the box method, we can do the same thing with the box. So on number 10, I'm going to do this in a box method. 3 minus the square root of 7, 5 plus the square root of 7, and I'm going to fill out my boxes. 15, 5 square root of 7, 3 square root of 7, and I get a negative square root of 49. I can do square root of 49. Turns out to be 7. So 15 minus 7 gives me an 8. And when I combine my like terms here, negative 5 plus 3, that gives me a negative 2 square root of 7, and I end up with another binomial, but it's in simplest form. The last one I put up here is kind of interesting. If you're really good with your factoring patterns, you might recognize this. We've talked about this previously, but these are conjugates. So watch what happens when I go through the FOIL or box method. I get a 25, I get a plus 5 square root of 7, and a minus 5 square root of 7, and a square root of 49. So I'm going to combine like terms right here, but they end up canceling. So I get 0 square root of 7. That one has vanished. I'm left with a 25 minus square root of 49 is one I can do. This is a radical I can answer. So 25 minus 7, so I took 2 radical binomials and multiplied them, and I got a real number without any radicals, These two things have a name. We've talked about this before, but they are called conjugates. Okay, this is our difference of squares pattern, where that middle term cancels out. So you got to be on the lookout for that. The reason I talked about this is the concept of conjugates is what helps us with dividing. Now, when we first started talking about radicals, we said we don't like having radicals on the bottom. So we went through a process called rationalizing the denominator. Well, we're going to do the exact same thing here, but it's a little harder because there's two of them. So we're going to take the lesson we learned right here. If I have two binomials that are conjugates, the radicals disappear. So when I go to simplify this, when I go to rationalize the denominator, I'm going to use a conjugate. Now, I'm always multiplying by 1. 1 does not change my answer, but I get very creative with what I choose for 1. So I'm multiplying by 1, not going to change my answer at all, but notice that I took the denominator and found its conjugate. So now when I multiply these two things together, I get a square root of 25. I can do that one. I get plus a square root of 10 minus square root of 10. That worked out nice. And a minus square root of 4. The square root of 10 is the only one I can't do in there. I'll adjust this for you. Those square root of 10s are the only ones that I can't do. So if I do the square root of 25 and the square root of 4 and subtract them, I have rationalized my denominator. Now the top's going to get messy. I understand that. Here I get a 3 square root of 10. When I multiply here, I get a 3 square root of 4. That's one I can do. Square root of 4 is 2. So 2 times 3 gives me a 6. Can't do much with that square root of 10. So I'm just going to leave it alone. I have a 6 and a 3 square root of 10. Great answer. Simplify a little farther. These all have a 3 in common, and they're all outside the radical. So I get 2 plus the square root of 10. The 3's would all cancel out. Great answer. Obviously no denominator to worry about. Definitely no radical on the bottom to worry about. And it works if only one of them is a radical. Okay? Still going to do the same process here. I've got a 6 plus square root of 3. I'm going to multiply by 6 minus the square root of 3. If I did this right, if I picked my conjugate correctly, I should end up with just a number on the bottom without any radicals. Not worried about the top. Top can get messy. Not worried about it. Okay, it is what it is. I just distribute the 11. But on the bottom, I get a 36. I get minus 6 square root of 3, a plus 6 square root of 3, minus a square root of 9. Perfect. The square root of 3's, the ones I couldn't do, they're gone. What's left is a 36 minus a 3. I can do that. I can do a 36 minus a 3. That gives me 33. This is a fine answer. It proves that there's no longer a radical on the bottom. You have rationalized the denominator. We're going to simplify this just a little. They all have an 11 in common. I'm going to take that out. So if I take my 11 back out, I get a 6, a square root of 3, and a 3. Now, notice I didn't simplify these. This is under the radical. This is not. They are not things that I can simplify, but I definitely got the square root off the bottom. There's my simplified answer.